Hello, welcome to SOH, the best office hours, because you're part of it. So let's get above 5 again. This is 2023, question number 4, Calculus AB. So we have a problem that let's go over. Let's have what we need to do and what are the main ideas. Maybe you have enough, and then I will go one by one. These problems are usually a bit long. They have lots of derivatives and integrals and things like that, and a mixture of different ideas. They are not terribly difficult, but they are, they take some time. So they say the function f is defined on a closed interval and satisfies this condition. So one of the first things is to notice that we will need to use that later on. Then the graph of f prime, this is very tricky. F prime, this is the graph of f prime. It's not the graph of the function itself, right? So be careful. This is not the graph of f. So that's the first thing that we need to be careful with. And then it consists of 2 line segments and a semicircle. Fine. Does the function f have a relative minimum? So this is something like this, a relative maximum, something like that, or neither at x equal to 6, so here. So we will check whether, you can see this is the function f, right? It looks like that. Whether the derivative, so the slope is here is negative, is going down, and then positive, or if it's first positive and then negative. You can see how this is the f prime. So it's always positive, so it will be neither, okay? Now, B, on what open intervals, if any, but open intervals, so let's not use the square bracket, we are going to use the open bracket. If any, is the graph concave down? Concave down is something like a maximum. So remember the derivative is going to be the derivative. It's going to be here positive and then negative. So it's decreasing. That's the key point, decreasing. The derivative, okay, not the function. The derivative is decreasing. So do you see any places where the derivative is decreasing? Yeah, here is decreasing and here is decreasing. So I mean here and here, right? So that's going to be the solution. Then finally, find the absolute minimum. This is long and tricky. The absolute minimum is not the relative one. It must be absolute. So it must be the lowest. Or if it would be the absolute maximum, the highest, the greatest value. But there is a procedure. Always look first for the local one. So in this case, local minimum, if there is any. And then look at the edges. What happens at the edges? Edge cases. And then with that, we will be able to solve that. So that requires, a little bit more of work. Let's go then one by one. If you had enough, great. If not, you can jump to the one that you want to hear more, or just listen to it all, because I always add more material that you can use in more difficult problems or in the future in college. So let's see. 4. First question, does it have a relative minimum? So what we need to know is at 0.6, what happens with the derivative? And this is exactly the derivative. If we want to write it properly, we should say, like, always get a little bit of points before, like 5 to 6, like 5 to 6. What happens here? Well, the derivative is positive. What happens after? You don't need to go to 8, just a little bit, that it looks like you are understanding the interval that you are considering. Also, the derivative is positive, so there is no change of sign. Therefore, it's neither, because remember that if you have like a maximum, this is the function, or a minimum, then the derivative is going to be positive first and negative later. It increases and it decreases. If it's a minimum, first it decreases and then it increases. But here we have no change of sign, so it's neither. Okay. Now let's move on. And what open intervals is the graph concave down? So concave down, remember, is like that. So it basically means that the derivative, the slope, here the slope is positive and here the slope is negative. You could also find where is the slope positive and then negative, but it's easy to say that it's just decreasing, right? It's going from a higher value to a lower value. Where is it decreasing? Well, let's choose. We see that here is decreasing. Remember, this is the derivative, and here is decreasing. So the tricky part is that this is the derivative and it's not the function. It's not f, okay? It's the derivative of f, derivative. That's tricky. But then the solution is open interval, so don't close it, from -2 to 0 and from 4 to 6. And that's it. End of the story. We got it. Let's go to the next one. So C, well, that's probably going to be kind of a 0 divided by 0, something like that, right? L'Hopital. So in that case, what we will do is the rule of the derivatives for the numerator and denominator. So what do we have here? Let's see. that limit is going to be 6 times f of 2 minus 3 times 2 divided by 4 minus 10 plus 6. So the denominator is clearly 0. So let's see, we get a 0 here. So we have 6 times, and then remember, we have this. So 1 minus 6. Yes, we have that. Now, the rule says that you have to take derivative of numerator and denominator. Do not take the derivative of what? Of the quotient. No, it's not the derivative of the quotient. No, it's numerator and denominator separately. So that limit equals it's going to be the same as the limit of x equals to 2. It's a cool thing to know whether you could prove that, whether you could prove a L'Hopital rule. You know, if you want, just write in the comments that you want to prove, and we can write a proof of how it works. It would go through the line tangent, let's say, and then you would see why is numerator and denominator independently and not the derivative of the quotient. In our case, this is the same as then the derivative of this minus 3, because 3x, the derivative is 3, and here we have a polynomial whose derivative is 2x minus 5. If now you substitute this thing here, you have this. So in principle, we need to know, right, how much is this guy. But that's not too hard because we have the graph of f prime. So you just go here and say, oh, that's 0. Yes, it is 0. So what we have is 6 times 0 minus 3 divided by minus 1, which gives 3. So that's the answer. The answer is that that limit equals to 3. So all this equals to 3. End of the story. And then the final thing is a bit longer because it says the absolute minimum. So that's a little bit tricky, you know, the kind of the absolute minimum. So first step is, remember, call for the local minimum. If it would be absolute maximum, the local maximum. So local minimum. Now let's focus on that. So if we focus on the local minimum, we need something like this. This is the function f. Be careful that this is different to f. So it's not this point, no. Okay, or this point, no. What we want is the derivative. So the derivative is, here is negative, right, and here is positive. So where does this function change from negative to positive? Here is positive to negative, no. But here is negative to positive, yes. And nowhere else. So x equals to 2 is a local minimum, okay? Now, how high it is? Well, f of 2 is 1 because we are told here, the wording, so great. The next thing is the edges. The edges, what are the edges here? So 8 and minus 2. So x equals to 8 and x equals to minus 2. Then always look for something that tells you, without doing a lot of work, what's going to happen. So look at x equal to 8. What happens here? They will always help us a little bit. So after x equal to 2, after the derivative is always positive, right? Positive, let's be positive. So this means that it's going to be increasing. So f is increasing. It's getting larger and larger. Therefore, f of 8 is going to be greater than f of 2. So it cannot be not an absolute minimum. Okay, so x equal to 8 cannot be an absolute minimum because it's even greater than 2. Could be an absolute maximum, maybe. Now, what happens at x equals to minus 2? Let's see. For x equal to minus 2, well, sometimes the derivative is negative, so it can be, you know, positive. So it's unknown. We have to look at it in detail. So that's where it becomes a bit longer. So, however, these problems are a little bit hard because you have to mix the derivative with the function that you want, right? You want f, but we have f prime. So we need to integrate f prime. That's kind of the idea in order to get f. So it's the area. This has to do with areas. So let's use the fundamental theorem of calculus. Like, wow, that's a fundamental. Yeah, and it is because it was a big step forward in solving derivatives and integrals, and it was found by Newton. So what we have is that the value of f at 2 minus the value of f at minus 2 equals the integral from minus 2 to 2 of f prime dx. That's the fundamental theorem of calculus. You know that this is equals to 1, and you want to find this one, but you have to get to know this, and this is area. So the area, which area? Well, So you can see that it's going to be this area. Let me plot it with a pink color, okay? Pink color. So it's going to be this area here, and this area here. Now you can see how indeed these two areas cancel out. They are the same. Let me use another color, maybe black. Let's see. Okay. Okay. So these two areas are going to cancel each other. So let's compute that. We have like the area, this area, and this area. They cancel each other. Okay. Now we still have this area, which is a triangle. It's a triangle. Now, triangle, the area of a triangle is base times height divided by 2. How much is the base? Well, 2. How much is the height? Minus 2. Well, be careful with this. Be careful because it's going down divided by 2. So you have minus 2. In other words, you know now that the value of f2 minus the value of minus f is minus 2. But this sign here is fundamental. Okay, super important. What you now can say is that the value of f of minus 2, as you can see, is going to be greater because that's 2. So it cannot be a local minimum, but we know this is 1. So if you want to look cool, this is 3. So in other words, x equals to 2, it is both, if you want, a local and, that's what matters, absolute minimum. And with that, you're going to get an absolute maximum of 5, which is great. Okay? Thank you, and see you in the next one. Bye.